Hi, my name is Dakota Willingham, and today I'll be presenting on the Moon 2 Saturn cargo launch vehicle I created. And so the basic mission profile is that Earth is facing an extinction event. So second decibel is occurring, crop blight, global food collapse, not enough food for the amount of people that there are. To offer solution to this, a wormhole near Saturn popped up, and it appears to offer access to a new galaxy and exoplanets, and these exoplanets could be a potential new home for humanity. And so the humanity already has a lunar base established on, and this lunar base enables the rapid 3D printing of solid rocket motors and their propellant. And so, if you could launch from the moon, the lower delta V costs from the moon to Saturn allows for these heavy, high G cargo launches. And so, this 3D printing of solid rocket motor propellant using UV curing processes would allow for this mission to occur very easily. And so the primary structure of this is a solid rocket booster. There's an internal solid rocket booster inside. That's what carries all the pressure of the booster. But the outside is the structure that we analyze to carry the axial loading and stuff like that. And so that is just a frame cross section with stiffeners, stuff like that. And so the this structure delivers high accelerations, about 10 Gs, and so that's for the injection burn towards Saturn. And also must carry a 12,000 kilogram supply slash payload module, and that is for taking this payload module would separate from the structure and then go out to Saturn, rendezvous with the researchers, and so nobody's on board this, and that's why it can achieve these 10 G high accelerations because there are no crew on board this vehicle. And so the structural loads that must be analyzed are axial acceleration, of course, also engine gimbaling, so any side kick from the gimbal will cause a sap force. Also reaction thrusters of the payload vehicle, that's 4,000 newtons for any additional control. And so for the design and the materials of this, the entire length of the rocket is 13 meters, and so that's 12 meters for the core. That's that constant diameter section that you can see on the bottom right. And there's also a 1 meter payload adapter, and that's where it caves in. That's 1 meter tall. So the diameter of the constant cross-section core is 3.5 meters, and the diameter of the top of the payload fairing is 2.5 meters. There's 8 longitudinal stiffeners distributed throughout this radially, and there's also 5 frame rings from the bottom base all the way up to the top where the payload is, and that's to resist any bending moments for the axial or the longitudinal stiffeners, and also any crushing forces to not allow the structure to cripple and stuff like that. So the materials used were TI6AL4V for the stiffeners. That's titanium alloy. This offers high strength to weight ratios. You can have less material for the stiffeners for higher loads. 2219 T62 aluminum. That's for the skin because it's lightweight, strong, protective. Um, and then the main engine gimbals, it was set to plus or minus 7 degrees, and was factored into the inertial loading. And so an example of the pattern model used for this analysis can be seen at the bottom right with all of the applied loads and the deformation.